Hello, old car people. This is a video on a subject that's been a bit of a bane for me, and I suspect it is for many other people. This is an ignition condenser, and for cars built with traditional Kettering points up to around about 1980, condensers are increasingly difficult to get as an OEM item. And so for people with older cars like myself that are regularly driven, we're increasingly having to turn to eBay and other marketplaces to try and locate old stock items of the correct properties, correct size, that are a like-for-like replacement with what was on the cars originally. But there are a lot of problems with these now because they're getting old. Some of the stock you can see here ranges between current through to 60 or 70 years old. So it's really important to understand, is this okay? How do we know if they work? How do we test them? And, how do they fail? And then, so what do we take from that? What are the solutions to these problems? So, we're having difficulty getting the right condensers. What's the best thing to do? Is it to get a new condenser that's not quite right? Is it to buy new old stock condensers? So I'm going to go through this problem using the example of early Holdens with Bosch ignition systems. So I'm talking about the period from 1953 to 1963. This is a common part to a lot of cars of that era. It's exactly the same, for example, in the Porsche 356 and through to the early 911. So in 1965, the Porsche 911, various other Mercedes and Bedfords and Internationals and Opel cars also used this or very similar part numbers. But really the principles that I'm going to talk through here apply to all condensers for all Kettering points cars from, really the period from the invention of the Kettering point system in the 1920s through to, their end in the 1980s. So the reason I'm making this video is that condensers have caused me a lot of grief, and it's taken me a while to figure out exactly what the problem is. And I've churned through a lot of condensers and coils, and I've even suspected incorrectly that I've had a carburetor problem. And so the summary version of this video is you shouldn't buy any condensers that are over 30 years old. Just forget it. Put them in the bin. If you've got condensers that are over 30 years old, put them in the bin. Even if they're new old stock, made in Germany, top tier, they're probably not worth fitting to your car. The amount of trouble they will cause exceeds, the value of the originality or avoiding cobbling something else together, because the reality is in many cases you will not be able to get the right condenser. You won't be electrically correct or mechanically correct. You'll have to cobble something to fit it on. I think there's evidence that a lot of people are struggling with this. There are replacement distributors now being made for early Holdens. I haven't seen any of these distributors with mechanical failures, a bit of wear and tear maybe, but I think there are a lot of problems that are attributable to having the wrong condenser. So, what is a condenser? Very similar, as I said, over a long period of time, pretty much over 60 years. So what I'm looking at here is actually from Dyke's Automobile Encyclopedia. This is from like 1935. And this specific ignition system we're looking at here is a Remy system, very similar to the Delco system, and they of course merged to form Delco Remy, which did the first model of Holden ignition, but it's very similar to the Bosch system that was subsequently used. And we see here all of the key components of the ignition. And and the first thing you can really say about ignition condensers, which you can see located in this case depicted inside the distributor itself, is that usually they look pretty solid. They look like a pretty solid passive thing, like a chunk of metal with a strong wire coming out, and they look robust, like a set of points or a kingpin bush or a wheel nut. They look like something that is robust and could last forever. But inside they're actually quite delicate precision devices with a finite life, and they're ruggedized to protect them and stop them vibrating. And so the mechanical attachment is very important, but that ruggedness is quite deceptive, because really they're not at all, and they are a perishable wearing item, like a window rubber or a brake cylinder cup. They perish and wear out, and that's part of what I'm going to talk about. So condensers are part of a tuned system. They are part of particularly the ignition coil. So they work together with the ignition coil and the contact breakers. And what they do, their key purpose is basically to pull the potential, the voltage between the contact points, to pull that potential together as the points open, so that both sides of the contacts are at as close a potential as possible as soon as the points open. And there's a few reasons for that. The first one is to stop point damage, but the second one is to maximize energy, to stop back EMF sucking energy out of the ignition coil and therefore out of the spark. So when the points are closed, when the ignition points are closed on the lobe, that enables both the condenser and the ignition coil to charge up. So a field forms in the core of the ignition coil, and the condenser takes on an electric charge as well. It's only a small charge, and when the points open, the inductive field in the ignition coil collapses, and that's what generates the spark. But as it collapses, it also produces what is called a back EMF, a back electromotive force. And that back electromotive force comes back down the wire in the reverse direction to the contacts. And so the contact voltage upon separating would rapidly spike again, were it not for the condenser holding some of the old charge in the same direction. So when that back EMF comes, the charge in the condenser fights against the current flow from the back EMF coming from the ignition coil and cancels out, so that there is near zero potential at the points when they open. So the aim of the condenser is to counteract the back EMF, to counteract that spike that reflects back out of the coil, so the contacts are almost immediately pushed back to an equal potential after opening, and that prevents arcing and burning, and it keeps the contacts cool. There are various attributes that are very important in this condenser. Condenser or capacitor, same thing. Condenser is actually an archaic term which is stuck in the automotive industry. Other sectors now refer to them as capacitors, generally in electrical engineering and electronics, but it is in fact the same thing. And a condenser is a capacitor. A condenser has capacitance, and that's its number one property, is its capacitance. But there are other aspects that are super important as well. One of those is the rate at which it can charge and discharge. So the rate at which it can tolerate rapid changes of voltage, and voltage flowing one way and then spiking the opposite direction. So that's called dV dt, the rate of change of velocity over time. Really important characteristic. Closely connected is so-called series resistance or equivalent series resistance, ESR. And that is a measure of effectively resistance that appears in series with a condenser, and that affects the rate at which it can charge and discharge. And finally, and often very correlated with ESR, is leakage. Now, a capacitor should present no DC conductance, no ability from voltage potential to flow from one side of the condenser to the other side of the condenser. It should take on a charge and then that's it. It shouldn't enable any current to conduct through it. And that's because between each of these plates, and this charge is stored upon the plates, they are surrounded by what is called dielectric, which is an insulative layer between the plates. And so if you're getting conductance across from one plate to the other, you get what is called leakage, which is kind of a form of, I guess, parallel resistance. And that leakage changes depending on the voltage at which the condenser is operating. So we've got capacitance, we've got the dV/dt, which is impacted by the ESR, and finally we have leakage. So, you know, there are actually 4 properties there that really matter. And I think that, you know, if the ESR and the leakage are fine, the dV/dt probably, you know, it's an inherent property of how the capacitor is designed. So you know, we don't need to really think about that one, but we do need to think about the other 3. So I guess to summarize on what a condenser is, like this one I've got right here, which is you know, to suit an FJ Holden. You know, they're to stop transient voltage spikes bouncing back out of the coil to the points. And this enables a maximum energy spark, and it keeps the contact faces of the points clean and low resistance and cool, and it therefore minimizes contact erosion and maintains tuning, that is of timing and of dwell angle, are maintained for as long as possible if the points are not wearing. And you know, if you've got a fault in a condenser, aside from sapping power, it will cause rough running, it will cause increased fuel consumption, you know, it will detune your engine, and you know, eventually it will overheat and fail. So to do the job it's meant to do, you know, you need it to have the right capacitance or energy holding capacity, and you need it to have all of those other properties that I talked about. And something else that's really important to keep in mind is, you know, you might think, oh, my ignition system is 6 volts or 12 volts, or, you know, most cars are 12 volts, obviously. But, you know, this capacitor needs to be good for much more than that, several hundred volts. You know, if you go through books like this one here, Dyke's Encyclopedia, you know, they talk about the back EMF coming back at, you know, at least a couple of hundred volts. You know, in other sources, you'll see it being described as up to 400 volts. I've got to be honest, I haven't measured it myself, but, you know, I kind of take their word for it. And, you know, if you look at books like this, it has a section on condenser testing, and it makes some pretty crazy suggestions on how to do that, including, you know, hooking transformers directly up to the mains, or connecting condensers directly to the mains outlet in series with a light globe in order to, you know, strike wires together and examine the color of the spark. And I would not advocate any of those ideas. I think it's crazy. Hooking directly up to the mains is not safe at all. there are lots of other crazy ways suggested to test condensers, and I'll talk about some of those in a bit more detail in a moment. And you know, including the ones that you find on YouTube, I think they're very wrong. So, quite a complex thing. A lot of properties are important, and you know, the big problem we've got is that what is available as new stock today, like this item we see here, bears little resemblance to the factory items, which I will soon explain. You know, they differ both mechanically and electrically, and you know, what we can find secondhand, new old stock, forget secondhand, even new old stock is really not worth your time. So it's a bit of a mess, and there's a lot of disinformation out there, which kind of brings me on to my second subject, which is what you'll find is that, you know, there are a lot of people who are honestly and, you know, in good faith trying to share their experience of parts. You know, there's a common observation that new parts from China are often junk, and that, you know, even under high profile brands like Bosch and whatnot, you know, they don't fit, they fail within a few weeks. You know, I think that, you know, whether you've got an old capacitor or a new one, or, you know, condenser, it's fair to say that if you have got a power problem, you've got misfiring, a rough idle, any of those kinds of symptoms, you should always suspect the condenser. Always suspect it. It's just becoming a really common reliability problem. And, you know, when I was first trying to diagnose the problems I was experiencing, you know, I was unable to get new condensers of the correct type. And so I was collecting new old stock ones, which, you know, I went through a few of those, and, you know, they fixed the problem a bit or for a while, but I still had, you know, reliability problems and points burning and whatnot. And so I did what you've done. I went to YouTube, I went to, you know, Reddit, I went to other places, I went to chat boards to try and figure out what is going on, you know, how are other people figuring out what's happening and you know, fixing the problem. And the ideas I found were terrible. And, you know, being an electronics hobbyist myself, I knew they were wrong. And the typical suggestions that you find go something like, use a multimeter like this one on ohm setting, you know, as an ohm meter, to charge up the condenser over its contacts, and then switch it to voltage, and then measure the voltage, and if you see a voltage and it drops, then, you know, the condenser's okay. So there's, you know, many suggestions like that, many videos on YouTube that suggest something like that, and you know, it tells you pretty much nothing other than the condenser is holding some voltage under that test condition. You know, it doesn't tell you how much or what the rate of charge is or what the internal resistance is or the leakage is. It tells you nothing about any of those other properties. It basically tells you nothing about any relevant property other than if it is completely failed, short or open. So, you know, as someone who likes to see classic cars preserved, I love to see cars like mine on the road and other people, you know, doing likewise and not having too much grief. I thought I better put together a bit of an experiment here and share my experience, and hopefully it makes it a bit less painful for others. So to be clear, you cannot check an ignition condenser with a multimeter using an ohm meter and a voltmeter. It's just it just doesn't do anything. It will tell you if the condenser is completely dead, but, you know, it is no more a test than to say because a car rolls, it's in peak roadworthy condition. So even for a typical capacitance meter will tell you very little. So this meter here that I'll use in a moment is actually a very good capacitance meter. But it still does not give you the full story. You need some more specialist equipment like this item I have here, which is a Heathkit capacitor checker. So I'll be using that in a moment to also kind of show you how these condensers fare, all of these new old stock condensers. So what I'm going to do is particularly work through these examples of these 4 condensers I've got here. These are all Bosch GB59 or GB61 condensers, which were retailed in Australia. What I'll do is I'll just rearrange things a little bit and get all the boxes open so I can just talk through them one by one. So here we go. We've got 4 condensers. So talking through these from left to right. So here we have a early 1980s Echlin. This is made in West Germany for Echlin in the US. Part number EP258 condenser replaces GB59 and GB61. It also refers to BC59 there, which is BC is a generic replacement of a GB59, which is a little bit confusing. The next one we have is a genuine Holden 7405514, which is also a GB59. This is the original 1960s article. This is a genuine Holden Bosch made GB59. Here we have a Lucas resold Bosch condenser. This one is from a bit later. This was from the 1970s, but as you can see, it's kind of, near identical form factor. Finally, we have a modern day Bosch GB61, and there it is. And so it's, you can obviously spot some immediate, obvious differences between the original early condensers and what is sold as a GB61 today. The other thing that I should point out that's pretty important, both for Holdens and a lot of other cars of this era, so the FJ Holden, like the Porsche 356, is a 6-volt car, and the FE, FC, FB, EK, EJ Holdens, EK/EJ Holdens are all 12-volt cars, like the early Porsche 911, which used the same condenser. I think it was only the first year, 1965. So what does that mean? Well, originally GB59 was sold as the 6-volt condenser and GB61 was sold as the 12-volt condenser. But it seems over time it's somehow been merged together, and I mean, as you can see, even from the 1980s, this says it's good as BC 59, 61, GB 61. So, they're saying this is 59, 61 are the same. And, if you look on the Bosch catalogue today, you'll see that GB61 is also nominated as the part for the 6-volt FJ Holden. So, my view is that it actually doesn't matter whether the car is 6 or 12 volt. It's probably irrelevant because the condenser is mainly about the back EMF, not the normal forward voltage. And the back EMF is so much bigger and is a function of the collapsing field in the coil. There are a whole lot of dynamic effects there which are much bigger than what the nominal input voltage to the points is. So, and to the coil. So just to kind of remove that from the picture, as far as I can tell, it's actually not really relevant. It may have been relevant back in the day. They might have had slight differences of capacitance, but the kinds of differences we're seeing now are so big by comparison, whether it's between old stock items or whether it's between new items, that I think the variability that you even see between options is so much bigger than the nominal difference between the GB59 and the 61 that you can just, forget it as a consideration. There are much bigger problems. So three of these are genuine Bosch. Two of them of which have been retailed under different brands. So these three on the right are all genuine Bosch, and of course we have this one OEM Holden branded item. So the first thing we note is that the physical packaging of each of these is quite different. So starting off with the original factory item, it's a single integrated spot welded steel housing. You see it's got this pressed bracket that is spot welded on to the condenser body itself, and that continues onto this later version from the 1960s. I mean, but they're essentially the same the same form factor. But mysteriously you get to the current day of a GB61, which is supposedly the same part number, and we've got this little cylinder with the Bosch logo there on top, and there is nothing to attach it to the distributor. We get a bit of a hint on what might have gone wrong here, because there was a period in the 1980s when condensers like this one were being imported, and this is still an integrated unit, but not as permanently as the other two items. So again, we've got this pressed steel bracket, which is identical in terms of mechanical mounting, but then we have a solder dot through the side of this condenser. And if we look at this item that Bosch now supplies, it is extremely similar to the German Echlin capacitor condenser from the 1980s. Diameter might be slightly smaller, but it's very similar. So I'll come back to what I think's happening there a bit later. But what we see here is a range of 60 years or so of condensers, some genuine and one not. So I don't know how Bosch thought this worked, as a GB61 replacement. I suspect that they were under the misapprehension that this part was common in Australia, as used on the Porsche 356 and 911. And I think they may have assumed that this bracket was, remained as part of the distributor or could be easily reused, when in fact in Australia, certainly right through the 1970s, and I think as late as the 80s, these integrated units were what were manufactured and what people have been using. So that makes things a bit difficult if you have one of the genuine style condensers and then you pick up one of these. It's sort of like, well, how do you attach it? That's a bit of that's something you've if worst comes to worst, you can cobble together your own bracket with a pipe clamp or something. But what matters even more is the electrical properties. So here's the test gear that I'm going to use just to run through what those properties are. Ideally, you also need to have a properly calibrated ESR, equivalent series resistance meter. You know, I don't have one of those, but this thing here, this Heathkit capacitor tester, gives a bit of an indication of ESR depending on how far this eye opens. So what this really excels at, though, is measuring leakage at the operating voltage of the capacitor. So it tells you, are the fundamental properties of the capacitor, its dielectric performance, are they functioning at the normal operating voltages which the condenser is going to experience? So the two meters I'm going to use are the EEV blog from Dave Jones, his Bryman BM2257 meter, which has a very good capacitance meter built into it. And then I will do a leakage check using this Heathkit capacitor checker. You know, I should also add that, you know, in a direct sense, electrical leakage in an ignition condenser, as measured by this machine here, isn't actually that important. It actually doesn't matter directly in the way that it matters in like a radio or electrical equipment. Like it doesn't mean you're going to destroy a power supply or break the tuning. Leakage is not a direct problem in an ignition system because it's just going to dissipate some of that electricity, some of that spike that's coming back out of the ignition coil. You know, it's going to dissipate it in a different way as heat rather than as storage, but it's, you know, it's still not inherently a big problem as in other applications. However, electrical leakage is an indication that the capacitor film or the paper, the dielectric, is breaking down. It means there is conduction through the dielectric, and it will therefore be heating, and it is on the pathway to failing, at which point its capacitance will rapidly drop, the leakage will climb, the ESR will climb, the condenser will start heating, and it will not be able to charge and discharge rapidly enough to do that job of stopping the sparking on the contacts, and then you experience all those problems: power loss, hesitation, hard starting, all those things that seem like they could be carburetor issues. Like, you know, it can lead you on all kinds of wild goose chases. So I think now what we've got to do is just work through these one by one. And what I'll do is I'll just work through an example or two and then show you the results, because, you know, this takes a bit of time and it's turning into a bit of a long video, a longer one than I expected. So I'm going to try and speed this up a little bit. I'll be back with you when I have got one of these ready to test. So here we go. First cab off the rank, the genuine Bosch item from Holden, the Holden branded GB59. And we are getting a capacitance of 361 nanofarads. So that is 0.361 or 0.362 microfarads. So capacitance, okay, that seems fair enough. That's pretty close to the typical values that people talk about. So now, I'm going to, excuse me while I put you down for a moment. Now we're going to hook up to a capacitor checker. Now that we know what the capacitance is. So, kind of expecting it to be somewhere on the scale here. We'll just do a little check. Now, even though I'm going to be looking at this as a capacitance reading, what I'm interested in is how much the magic eye opens here, because that gives us an indication of the health of the condenser. So you can see the magic eye has a dark patch at the bottom, and if the capacitor is really healthy, we see a wide opening of that eye when we are measuring the correct capacitance. And if there is a problem with internal resistance, then that opening gets very small. So I'm going to switch this into bridge mode. We are on C times 1, and now you'll see the eye is completely solid green all the way around. So what we're looking for is where it opens, and it's meant to open somewhere around 3.6. So I'm not getting any opening in that area at all. So let me just try adjusting the power factor a bit, which can help. Oh, there we go, we're getting a bit of opening. Oh, crikey, not much happening there. How much can we get it to open? Yeah, so by adjusting the power factor a little bit, I managed to get a bit more opening, but not much. That's peaked. That's peaked right there. So, and what we're reading is, yeah, just over 0.35. So, like I said, 0.361 is what the capacitance meter said. So this is telling us the same thing. It's telling us the capacitance is the same. So now comes the interesting bit. How much does this capacitor leak? So we've got a bit of a warning. It looks like it's got a lot of internal resistance. It looks like it's got a bad ESR. So I have not got high hopes about this. What we're going to do is we're going to switch this to paper and mica. So this sets a threshold on leakage that we would expect from this type of capacitor. And that's what these capacitors are. These are a film capacitor. I suspect they're actually paper, and that's why we've got this leakage problem in old age. But you know, they're certainly not electrolytics. They should have very low leakage. They should have very, very low leakage. So what we'll do now is we'll switch across to leakage settings. We'll start at the lowest voltage, which is 3 volts, which is lower than the rated voltage, and we will go to leakage. And what we see is that the eye opens, but quite slowly. So I'll switch it again. I'm on discharge, and we'll go to leakage. The eye shuts, and then it opens. Okay, let's try turning the voltage up. Now we're on 6 volts. Even at 6 volts, we've got leakage, and it's eventually opened. Now we're at 10 volts, and it's not opening at all. Okay, so that's a bad sign. Let's figure out how bad this is. So let's switch to the miniature electrolytic setting, which increases the threshold from 2 microamps of leakage up to 15 microamps of leakage. So that's way more. This should provide heaps of buffer. And now we'll keep putting the voltage up. That's opened again. Oh, it's slowing down again already. 25, even at 25 volts. So remember, this is meant to work at up to 200 to 400 volts. Now we're at 50, and it's not opening. We've hit the wall. We've hit the wall. Look, I'll just try switching to electrolytic just to test it against a 25. Actually, crikey, I can't remember what the electrolytic threshold is. It's a lot higher. It's ridiculously high. It's like, I think it might even be like a milliamp or something. So let's just to see how bad it is. Okay, it's staying open now. 400 volts. Oh my gosh. Okay. Even so, now it's closing up on us at 450 volts. Even on the electrolytic setting. Okay, that's not good. This condenser is not performing well. Now what I'm going to do is I'll go through all the others. I will go through them all just to see whether this one is uniquely bad. Let's measure the capacitance of this new one, just to give ourselves a comparison. doing this with one hand, but let's see if I can figure it out. I've smashed my thumb so hard recently that I have been having to operate with one hand for a while. So, okay. So this is reading as 253 nanofarads, or 0.253 microfarads. That's a bit lower than I was expecting. That is quite low. I think, you know, if you read about these, you know, they're typically around 0.3. So that's a bit of a surprise. Give me a moment and we'll come back to do the ESR and leakage test. So I've got this hooked up now to the capacitance meter. And I'm ready to go again. So let's start off with doing the actual test. Let's see how the eye opens when we check the capacitance. Okay, the eye has shut. Let's just dial this. Holy moly, there we go. Look at that. That's good. That's solid. And we've got no power factor correction there. We've got good eye opening there without any mucking around. So that's, you know, it's sharp. So that looks good. And what are we reading here? We are reading about 0.25. I mean, that's about 0.25 microfarads. What did I say? It was on the other meter it was 0.4. Sorry, sorry, I'm misreading this. This is about 0.25, and what we read on the capacitance meter was 0.253. So that's great. That is bang on. So right, now that we're happy with that, we can go across to discharge. So again, we are on the paper capacitor setting, which is for a maximum of 2 microamps of leakage. Then we switch to leakage mode, and now the volts are pumping. Okay, starting off at 3 volts. 6, 10, 15, 25, 50. The eye is opening instantly every time I switch it. 50, 100, 150, 200, 250, 300, 350. Or is that 400 if I missed one? 450, 500, 600 volts. Discharge, charge, it's instant. There is no leakage in this condenser at all. It is nowhere near 2 microamps even, all the way up to 600 volts. And it hasn't warmed at all. It is in discharge mode. I'm not going to give myself a 600 volt shock. Yeah. And let's just check I haven't overdone this. We'll just go back to bridge mode and make sure that the condenser is still, yeah, there we go. The capacitance is still good. Yeah, that's what I'd expect. The behavior of this brand new one, for its leakage and its you know, this rough measure of ESR, it's looking perfect. Capacitance is a bit low, so let me go away. I'm going to measure all the others and I will tell you what they are when I'm done. Okay, I've completed all of the tests, and here we have the full list of each of the results for the condensers. So on the left hand side we've got the part number it was that I tested. So we can see starting from the top, or in order of year. Actually, I've switched this to start with the oldest first. So about 1960, 1970, 1980 and 2024. So running through from the top, first thing we notice is the original Holden one has quite a high capacitance, 0.361 microfarads. So it's the highest of all of them. The other old stock capacitors, you know, they're ranging from 0.300 to 0.361. So that capacitance is quite different to the 0.253 of what is today sold as the Bosch GB61 at the bottom. So not completely sure what that means. I have some ideas. I'll come back to that in a moment. So the next results, leakage. So as I said, the first old one, the leakage was pretty bad. You know, it hit 2 microamps at only 6 volts. So it failed the paper capacitor threshold at only 6 volts. And it failed the miniature electrolytic threshold at 25 volts. That's 15 microamps of leakage. So that one has dielectric problems. It's not good. The next one, which is also a Australian-made Bosch, resold under Lucas, and you can see the Lucas part number there as well. So it came in with a better result. With it got all the way up to 15 volts before failing the 2 microamp test, and it got up to 50 before it failed the 15 microamp test. So, you know, that one, it's kind of okay. I think that one's got a bit of a road ahead. And when you also consider that the eye opened very broadly and quickly and clearly, makes me believe that the ESR is probably okay still on that 1971. Similarly, the 1981, which is the Echlin made in West Germany, it comes in at 0.321 microfarads. It got up to 10 volts before failing the 2 microamps. Now keep in mind, this condenser is meant to be on a nominal 12 volt car, like a Holden FE to EJ or a 1965 Porsche 911. So it's meant to be operating on 12 volts, but we even see at 10 volts it fails the 2 microamp test, and at 25 volts it fails the 15 microamp test. But again, you know, eye opens clearly. I didn't need to apply any power factor correction or anything to get the eye to open. So again, I think that you know, its ESR is probably tolerable, but the dielectric is clearly deteriorating. And where we see that most vividly is when we compare it with the current Bosch GB61, which goes all the way to 600 volts against the 2 microamp threshold and never gets close to failing it. There is absolutely zero leakage. So I think what we can conclude is that all of these old stock capacitors, these new old stock capacitors, are probably paper capacitors. I think they're probably made from, you know, like Japan wax paper, like the paper capacitors in radio equipment. And they're failing from the same failure mode that we see in those, and that is atmospheric moisture absorption into the dielectric, which makes it conductive. But also, as I've recently learned, it can also push capacitance up. And so I think we might be seeing some elevated capacitance, particularly in this oldest one that's measuring at 0.361 microfarads. I think it's measuring high because the dielectric properties have changed with the water absorbed into it. But, you know, with that level of leakage and that terrible ESR, this condenser is not going to work properly and is going to cause grief very rapidly. And, you know, these two, given their leakage, I think are very close behind. So that's my conclusion on what's happening. These old capacitors that are more than 30 years old, we have to forget them and move on. I mean, I've probably sunk, you know, I've got more of these. Actually, this is a small sample. I have spent hundreds of dollars collecting condensers to run this experiment over the period of a couple of years. So let my lost money be your gain, and know that there is no point in buying these except under some extremely niche enthusiast circumstances, which I can come back to in a moment. But generally speaking, I would say forget these. The leakage is way out of range for what you would expect for a condenser. The resistance and leakage is almost certainly accompanied by a big deterioration in their tolerance of dV/dt. That is the rate of change of velocity, the rapid rate of change of voltage over time. And I think for that reason alone, even this Echlin capacitor, which is only about 40 years old, I think it is inadvisable to use them. So, does that make this a clear winner? We can't attach it. It's the wrong shape. Doesn't look anything like the OEM Bosch GB59 item. There you can see, just to confirm again, there it is. It says Bosch on it. It's Bosch Australia. It's got the little Bosch logo. And this is absolutely Bosch, but somehow or other the GB59's gone from this to this. So putting the mechanical things aside, the electrical properties of this are superb, but the capacitance is very different to the old stock ones, and is possibly not correct. I was kind of expecting something like 0.3. Now, it's possible that all of these, whether they are 60 years old or 40 years old, have drifted up by similar amounts. Maybe they were 0.253 microfarads new, and they've drifted up 50 to 100 microfarads. I've looked at a lot of old capacitors, and I don't think that's right. I think the value of this is actually low. I think Bosch has probably stuffed up, just as they have with the form factor. So not ideal. And my expectation is that is simply because that this is a common value for a whole lot of cars in Europe, and it's the closest thing they could find to what they thought they would suit. The replacement of the GB61 in the Australian market. So I think they have probably got it wrong, but I think that difference in capacitance. So the lowest of the the original Bosch we saw was 300 that is 0.300 microfarads in the case of the Lucas, and this is 0.253. So we're talking about a difference of about a sixth. Not great. Really, you have to check the point where to form a view on whether it was okay or not. Maybe look at it with an oscilloscope. But I would suggest that problem is not as big as the problem of leakage. So my guess is that it is preferable to have a condenser with a capacitance that is a bit off, a bit low, rather than have a capacitor that is leaking, has failing dielectric, and is on the path to failure. So yes, having a condenser that is off the capacitance by 20%, I think, is better than the leakage, because you will be on the path to failure, as I have been with multiple new old stock condensers. So if anyone out there's got any suggestions, maybe there's a different condenser that you know about for a different car, maybe for a Holden red motor or a blue or a black or something like that, maybe something for a totally different car. Maybe you've got a capacitance meter and have checked. Tell me about it, and I would like to get hold and try other condensers. So I guess just to wrap this up, I guess what I'd conclude is that there are no perfect solutions. I'm sorry. And any condenser over 30 years old should probably go in the bin, even if it's new old stock. And what we're seeing in these examples that I've tested and others is, they're just not going to last. So I now know why, having tested the leakage on this leakage meter, which I only finished rebuilding, a couple of weeks ago. The reason is that the dielectric is failing, and that causes me pain, because I like having an original car and having an original OEM made in Australia Bosch condenser. I love that. I love those details, but I'm not going to do it at the risk of getting stranded in the in the cross city tunnel or whatever, or some other underground freeway. It's just not a risk that I can afford to take. So I will not be using that. Bit heartbreaking, bit of money down the drain, but it is what it is. Also, another conclusion, don't worry about the difference between 6 and 12 volts. They used to be separated by the GB, the 61 and the 59 in this example. It just doesn't matter. Compared to these other issues, it's just noise, forget about it. The other thing we can conclude is that Bosch has no idea what the GB61 or 59 is meant to look like. It does not attach to their own distributor, so they've obviously lost some corporate memory there, and they probably have the capacitance a bit wrong as well. So not great, but I think it's probably the best we can do. Finally, a pro tip specifically for early Holdens, going back to what we see here, the similarity between this made in West Germany Echlin GB61 and the modern GB61 being very, very similar. I'm going to reuse this bracket by unsoldering it and putting it onto the new one. And if you can get hold of a GB59 or 61 in this form factor, then you've got a lot more options. It's not original, but it's usable, and it's going to mount straight up nicely. It wraps around a bit like a hose clamp. You can push the terminals in and clamp it in, possibly without even soldering it. But having good electrical conductivity is really important, so I'll probably still give it a quick hit of solder anyway. But it turns out this bracket is in fact available as a separate Porsche part number. So if you look for the Porsche part number, and I'll put it in the comments so you can copy it out, it's 616.602.900.00. That is this exact bracket that we see here, which will fit onto, or will just about fit onto, with a little bit of prying, this Bosch part that is sold as GB61. So look up that Porsche item. You can you don't have to tell anyone that your Holden has been partially contaminated with a German Porsche part, but actually these cars share a lot of parts. Like the generator regulator, for example, the original 6-volt generator regulator is pretty much the same as the Porsche 356 Pre-A, same voltage and current ratings. So I'll include those other tips. So there you go. It's been a bit of a long video. I hope you found it informative. I hope it helps you solve some ignition problems and keep your old car reliably on the road. Take care.